Lesson 2-1, Relations and Functions. Here's some review on the Cartesian coordinate plane. First of all, the x-axis is the horizontal axis, and the y-axis is the vertical axis. The axes are perpendicular, and they divide the plane into 4 quadrants. I'll label them over here. This is quadrant 1. This is quadrant 2. This is quadrant 3. And this is quadrant 4. We can graph points by ordered pairs. Remember that the x value is always first, the y value is always second. And another fun fact, the Cartesian coordinate plane was named after René Descartes. More vocabulary for you. The domain is the set of all x values or inputs. The range is the set of all y values or outputs. Another list of vocabulary where it's here. A relation is any set of ordered pairs. A function is a specific relation in which there is only one range values for each domain value. In other words, in a function, the x values do not repeat. That's the easy definition. A mapping is a diagram that shows how the members are paired. A one-to-one function means each element of the range is paired with exactly one element of the domain. And an easy way to remember that is in a one-to-one function, the x values and the y values do not repeat. So here's some examples. The first 2 relations below are functions. The third relation is not a function because -3 in the domain is paired with both 0 and 6 in the range. So there's an example of an x value that repeats itself and has 2 different range values. So these are all mapping diagrams. They show the domain and range values in separate bubbles, and then you draw an arrow connecting the x value to its corresponding y value. Only this first one is a one-to-one function because in this one, each x value and each y value are paired individually. One way you can tell if a graph is a function or not is by using the vertical line test. If a vertical line passes through 2 or more points, then you know your graph is not a function. So if I show you these 4 graphs below, this first graph here is a function because a vertical line is only going to cross at most one time. This W-looking graph is also a function because a vertical line will only pass through one point of the graph. This Z-looking graph is not a function because you can see that the vertical line is passing through 1, 2, 3 different values. What that's saying is for this specific x value, maybe it's -4, there's 3 separate y values paired with it. That's why it's not a function. And obviously a vertical line is not a function because it does not pass the vertical line test. Here the vertical line is crossing every single point on the graph. Discrete relations, these are individual points. When you graph them, you simply plot the points and you do not connect them. A continuous relation can be graphed with a line or a smooth curve. Discrete, continuous, 2 different kinds of graphs. Okay, let's try an example. The number of employees a company had each year from 1999 to 2004 were 25, 28, 34, 31, 27, and 29. State the domain and range of this relation, then graph this information and determine whether it represents a function. Is this relation discrete or continuous? Okay, there we go. Now I've got the correct view of the screen. All right, so the first thing that we want to do is create a table. In this case, the x values are the years and the y values are the number of employees. Okay, so from 1999 to 2004, those are our x values. Let's go ahead and fill them in the table. So we've got 1999, and that year we had 25 employees. Then we've got 2000, and there were 28 employees. In 01, we had 34 employees. In 2002, we had 31 employees. In 2003, 27 employees. And in 2004, there were 29 employees. Okay, so we've made our table and now we're ready to graph the information. I've got the years along the X and I went up by 5s on the Y-axis. So in 1999, 25 right there. In 2000, about 28. In 2001, 34. In 2002, 31. 2003, 27. And in 2004, 29. Okay, so now let's take the domain and range of this relation. When you write your domain and your range, you want to go in order from least to greatest. So the domain values are the X values in order from least to greatest. And I'm going to list them right here on the graph. So my domain are the years from 1999 to 2004. And to save on time, I'm not going to list them all. Those are the X values. To state the range, you're simply going to list the Y values in order from least to greatest. And so these I do need to list. I've got 25. The next one is 27. Then 28. Then 29. 31. And 34. Those are my range values in order from least to greatest. Domain, X values, range, Y values. The other part of the directions, state whether it represents a function. Does this represent a function? And the answer is yes, because each X value is paired with only one Y value. So yes, function. And the last thing we need to do is say if it's discrete or continuous. This is definitely a discrete graph, because we're plotting specific points here. We haven't connected them with a smooth line or curve, so this function is discrete. Talking about information at specific points here, specific years in this case. Okay, and that's all we need to do for this one. Let's try another graph. This time we're going to graph the function y equals 2x plus 1. Find the domain and range. Determine if it is a function, I kind of gave that away, and then state if it's discrete or continuous. Now in this case here, we aren't given any specific X or Y values, and so I suggest that we just start with the standard 5, -2, -1, 0, 1, and 2. Those can be our X values or our inputs. So in the table here, it's good to have a couple negatives and a couple positives, and of course centering around 0 is going to be the easiest. Okay, so you pick your X values, your inputs. Now to get the Y value, you go up to the equation and you plug in X. So to find the Y value, I'm going to take 2 times the X value and then add 1. So for -2, 2 times -2 plus 1 gives me -3. Then my next X value is -1. I'm going to take 2 times -1 and add 1. That gives me -1. Then I'm going to take the next X value, 0. 2 times 0 plus 1 gives me 1. 2 times 1 plus 1 gives me 3. And then my last X value is 2. Remember, that's what I'm plugging in for X. So 2 times 2 plus 1 gives me 5. You can kind of tell that there's a pattern in the Y values here. They go up by 2s. Now over on our graph, -2, -3 is down here. -1, -1, 0, 1, 1, 3, and then 2, 5. Now in this case here, I was graphing an equation and I can plug in any value I want to for X, and so I do need to connect these points, because if I wanted to, I could plug in -3 and I would get -5, and this pattern would just continue on forever and ever and ever. So we do need, I lost my pen. We do need to connect these values, these points, with a continuous line. Okay, I think that's where we're at. All right, back to the pen. Actually, probably easier if I just draw a line. Oh my goodness. Let's try this again. Let's try this again. There we go. Okay, so we do want to connect these with a line because I'm graphing an equation and we can plug in anything we want to for x. So that line will continue on forever. All right, is this a function? Well, does it pass a vertical line test? It certainly does. There's no vertical line that will cross more than once. So yes, we've got a function. This is not working. Okay, there we go. Yes, we've got a function. And finally, is the graph discrete or continuous? It's continuous because we graphed a line. All right, you're going to see that when you're graphing equations, your graphs will be continuous. And if you're graphing specific values or data or information, typically then it's discrete. Okay, last thing in this lesson is function notation. We typically use function notation instead of writing y equals, we write f of x equals. But just remember that when you see an equation written in function notation, f of x really represents your y variable. Okay, so take a look at this example. Y equals 2x plus 1 is written as f of x equals 2x plus 1 in function notation. We can also use different letters. Sometimes G and H are used, and you would just read it as G of x equals 2x plus 5. So remember that that function notation is really replacing the y equals. All right, here's an example of where we have to evaluate a function written in function notation. So given f of x equals x squared plus 2, find each value. Well, they want us to find in letter A f of negative 3. Now, negative 3 here is really just replacing the x value. So what this means is plug in negative 3 for x, okay? And if you look at our function, it's x squared plus 2. So instead of x, I'm going to use negative 3. That's our input value. And then I'm going to add 2. Well, negative 3 squared gives me 9, and 9 plus 2 gives me 11. So what this means is f of negative 3 equals 11. If I wanted to write it as an ordered pair, it would be the x value is negative 3, and my output, the y value is 11. That's function notation. In letter B, we're plugging in 3z for our input, for our x values. So we're finding f of 3z. That means replace x with 3z. All right, so it looks like this. Instead of x squared plus 2, I'm going to take out the x and plug in 3z. So I've got 3z squared plus 2. Now, if I'm going to take 3z squared, that means 3z times itself, times 3z. And what do I get? I get 9z squared, and then plus 2. That's really all I can do. I cannot combine these together because I've got a variable in the first term. So 9z squared plus 2 is the new function, f of 3z. That's it for lesson 2.1. I've got 2 problems for you to finish tonight. We can check them tomorrow in class. Practice graphing this one here, and then also try these function notation problems.